Okay, then we move to our next speaker. Our next speaker is Professor Chunyi. Professor Zhi is now a full professor in the Department of Material Science and Engineering from the City University of Hong Kong. Let me give a brief introduction of Professor Zhi. Professor Zhi obtained his PhD degree in condensed matter physics from Institute of Physics, Chinese Academy of Sciences. After 2 years postdoc at the National Institute for Material Science in Japan, he was promoted to the permanent senior researcher in the institute. Professor Zhi has extensive experience in flexible energy storage, aqueous electrolyte batteries, and zinc-ion batteries. He has published more than 400 papers with an H index of 108 and a citation of over 40,000. He has been granted more than 80 patents, and Professor received many awards, including the President Award of CTU, and he's also the highly cited researcher since 2019. And he's also the RS Fellow and the member of the Hong Kong Young Academy of Sciences. So without further ado, let's welcome Professor Zhi to give the talk on the zinc-ion batteries. Professor, please.
Okay, thanks for the invitation. And also, let me see, thanks for the invitation and thanks for the introduction. So my name is Chunyi. So my topic is different from Professor Xu. Actually, I will talk about batteries, in particular zinc batteries. So I use a question as my title because we have been studying this field for several years. We noticed some problems happening in this field. So I would like to still start from this page. This is major projects running in the world, actually. In the past and the coming years, you will notice that all of these huge projects on batteries, they focus on lithium-ion batteries. They focus on the number of energy density, or as a specific energy. That's always tell about a story that for electrical vehicles, for example, the energy density is always not high enough. Then we look for some strategy to solve the problem of energy density. All of these projects work on this. But on the other hand, actually, we are also having more and more accidents caused by lithium batteries. Previously, we started from tertiary batteries, but we got many fire for EVs, for electrical vehicles, for EVs, for large-scale energy storage systems. And in the statistically, published a few days ago, that in China, the first 3 months of 2022, this year, actually, we have 640 cars, EVs, got fired, even within only 3 months. Although we have changed from tertiary batteries to lithium ion phosphide batteries, we still have this kind of accidents. And this is not for EV, but also sometimes for energy storage systems. So this kind of disaster, let's call it disaster, that you don't have time to rescue, and you cannot rescue. If you rescue, you got the smoke is quite poison. So if we analyze application scenarios for batteries, well, in the past years, people focus on the cars, mobile phone. So these two products, say, they require high energy density because they always run on the road. But on the other hand, if we go for large-scale energy storage system combined together with renewable energy or household energy storage, that if we use batteries, that we will face the scenario that many batteries taken up in one place. And you know about the lithium battery, if one battery catches fire, plus some wrong way, they can be very dangerous. The whole system will be broken up. And household case, of course, we need a smaller battery, but sort of safety might be an important concern. And another case, for example, is called the electric screw. That is very convenient. Use lithium battery, very light and very convenient. That we take it back to home to charge. Then you don't expect one day that it will be like this in your sitting room. Okay, if you compare lithium batteries with zinc batteries, lithium batteries, in terms of the material systems, graphite is stable, but if you intercalate lithium ions into graphite, it will be very active. Cathode is lithium metal oxide. Sometimes it can release oxygen at slightly high temperature, which can facilitate the combustion. On the other hand, the electrolyte is organic, which has almost the same ignition points close to that of gasoline. So lithium batteries generally is a very high energy system, but it's very dangerous. Intrinsically, in terms of materials, is very dangerous. We have to admit that so far that lithium batteries has been the safety of lithium battery has been improved that much, but intrinsically, fundamentally, it is not safe. If you go for zinc batteries, it's aqueous electrolyte system. Aqueous solution is for its extinguish agent, and if you put zinc and metal oxide in the water solution, that is intrinsically a very safe system. But energy performance is nothing compared with lithium batteries. That's why we don't expect a zinc battery can be used for EVs. For some other applications, it might be possible. For large scale systems, you don't need that high energy density. You probably will consider zinc batteries. But then, if you go for zinc batteries, actually in current days, that in terms of the cathode electrolyte, they are not very stable actually, and the anode side is even more problematic. So many issues. We always claim it has dendrites, but back to 2018, for example, the initial study for the dendrites of zinc batteries in the moldy electrolytes. We're not quite sure about it. Is there any dendrites for zinc or not? We always see a lot of paper published for lithium batteries. They claim lithium dendrites is a big issue for lithium batteries, but at that time that actually zinc has dendrites or not, we're not quite sure about that. So I ask my students, before we start to develop any strategy to solve the problem of zinc dendrites, I ask my student to invest. Do zinc dendrites exist in neutral or moldy electrolytes? So zinc batteries is not new technology. I say it's quite old actually. Nowadays, dry batteries still use zinc. We call it zinc manganese oxide or zinc carbon. Technology is based on zinc, and then people start to make it to be rechargeable. For example, this example is use alpha manganese oxide together with zinc sulfate as electrolyte to make it to be rechargeable. But then after that, this is my research. We use carbon nanotubers mixed with zinc with manganese oxide and use a hydrogel electrolyte, improve the cycling stability to be 1,000 times. Even the zinc anode has no any treatment, or let's say zinc anode is still quite stable in this system. So I got confused that is there any zinc dendrites in the moldy electrolyte? So I asked my student to investigate. Put zinc anodes as a symmetrical batteries, then you will find that has different current density. The cycling number, the time is quite different. If you increase the density from 1 to 10, the cycling time from 120 to let's say 1 level, you will see with the increase of the current density, cycling time is getting decreased much. So that means sometimes that if you claim there's no dendrites, it is possible. If you claim there are dendrites, it is also possible because you have different conditions. If you go further, you will see that at different, even the same current density, 5, for example, 5, if you go for different areal capacity from 0.1 to 0.5, you see the dendrites are totally different. That means at different capacity, you will see different dendrites behavior. High capacity means high loading mass of cathode. High capacity, you will have even severe dendrite growth. So this study tells us that if you we cannot directly say is there dendrites for zinc batteries. It can have dendrites, it can have no dendrites. It depends on the testing condition. But if you want to develop practical applicable practical usable batteries, you need high you do need high loading mass. You do need high current density as a rate capacity. That in that case you have the dendrites. Having the dendrites, so we're trying to solve the problem. This work we didn't start from dendrites. Actually, we started from it's called graphdiyne. This is a new materials. I've been looking for this. I've been focused on, I've been thinking about these materials for a pretty long time. Usually we synthesize these materials use copper as a catalyst. But in our lab we have a lot of zinc. When we're trying to synthesize these materials, we notice that if you put zinc in the solution, you also synthesize graphdiyne on the surface. You see the color change. Then the graphdiyne has a channel structure. So it will redistribute the zinc ions that you see in the symmetrical battery with the coating, the blue one. You get much better stability. Although you see the current densities are not that high. Then we change to another material, zinc fluoride. This is a copy from lithium-ion batteries that fluoride always gives you the stability, and they can be conductive for the ions. We synthesize zinc fluoride on the surface. Use symmetrical batteries to test up to 5 milliampere semi-square that you can have pretty good stability. And this one is not conductive, so it can avoid the electric conduction between zinc and water. If you don't have this coating, you have the hydrogen bubbles. If you have this coating, it can be it will be no more hydrogen evolution anymore. So if we use conductive, so we come to here. If we use conductive coating, that it cannot avoid hydrogen evolution, but it can be good for kinetics. If we use insulating coating, we don't have hydrogen evolution, but we will sacrifice kinetics. So in this work, we develop a kind of gradient coating with zinc fluoride and alloy on the surface. Zinc fluoride and alloy coating. That one we keep the good kinetics. And the hydrogen evolution, you see the gas come out, but with our coating that you don't have gas. This is gas evolution, the pressure induced by the gas. With our coating that you don't have a gas anymore, and more like uniform structure of the surface. This is based on the coating strategy. But after that, we think more that coating can be one solution, but it seems that it's not very effective if you go for high loading mass and high current density. We also think about organic. We also think about solid state electrolyte, or should we use zinc foil or zinc powder, or should we use organic or different pH values variation, for example, different method to solve these problems. The solid state batteries the idea from lithium batteries, we use solid state. In the beginning, I'm trying to use ceramics, but until now, I didn't find any ceramic organic battery, ceramic-based electrolyte can be useful for zinc because zinc is difficult to diffuse. Then, but polymer, if we in situ polymerize some polymer with low molecular weight, we can have very good interface. This is non-in situ polymerized one. This is how we optimize. No, this is for batteries with this polymer electrolytes that we can use. We can only use PBA to as anode. Zinc, magnesium oxide, and vanadium oxide is not very attractive in this case if you use solid state electrolyte. But stability is very good, but you sacrifice the kinetics, so readability is not good actually if you use solid state batteries. We're also trying to solve this problem with solid batteries. Another issue is storage life. Sometimes we'll call it shelf life. Shelf life means you assemble a battery, you store it at different temperature. If you see that even you don't test, if you don't do cycling, that after a few days, 1 week, say, you will see the capacity will lose. And zinc, put in mild electrolyte, you will see something growing on zinc, especially when the temperature is getting higher. Let's say the storage life of zinc battery is not good. If you change to solid state electrolyte within 90 days, the stability is quite good. Stability quite good for 90 days. Again, I have to mention that we sacrifice the kinetics with the solid state electrolytes that you generally you cannot have very good readability. Another issue is, should we use zinc foil or zinc powder? Because we always use zinc foil. I think 95% of the research work use zinc foil as an anode. The point for zinc foil is quite convenient. You just cut a piece of zinc foil, use it as an anode. But the problem is, if you go for very thin foil, so zinc is not very expensive, but if you go very thin foil, you'll see much more expensive. And adjustability is not very good. If you want to adjust the NP ratio, for example, your zinc foil, you don't have you cannot have continuous different thickness. And also the current collector and active materials, if you use zinc foil, current collector active materials all together, right? Zinc foil work as an active material, also current collector. At a low zinc utilization, it will be fine. But if you go for high zinc utilization, you got a big problem. You got a big problem because the conductivity can much worse. And if you go for additives, it's difficult to add additives to zinc foil. So we try powder. But if you go for powder, powder has large surface area. So you have the big issue of hydrogen evolution. You see that, so the zinc powder, zinc P is zinc powder. If you use copper as a current collector, that even without cycling, only for storage, you got the evolution. And even you put this zinc powder coating on the copper current collector, you see the gas evolution very severe, and the zinc particles getting broken in short time. And if you investigate the failure model, that if you use zinc foil, that you got short circuit after certain time. If you go for zinc powder, the failure model is different. It's getting more like polarization getting increased very fast. It's not normally like you got a short circuit, but of course, if you keep doing this cycling, you still have short circuit. But before short circuit, the polarization is getting much severe because for each particle, you got something growing on the surface. The particle will separate from particles. The contaction between particles, conduction pathway is broken. So we're trying to solve this problem by coating couple with tin, that couple itself as current collector and a couple coating with tin, that you will see the problem is partially solved. I'm not saying it's totally solved. You still have hydrogen evolution, but much better with the coating. And also the current, even after certain amount of time, for example, 120 hours storage, that is stability of the capacity is getting much better. And this is also without coating. This blue one, after storage is much worse. But if you coating with tin, it can be improved a lot, although it's not 100% solved. On the other hand, we focus on the zinc dendrites for planar structure batteries. But if you go for flexible batteries, for example, if you fold it, then you will see that planar test it can go, for example, 100 hours. But if you fold it, the short circuit will happen in very short time. And if you look at this morphology from here to here, that you will have large size dendrites on the surface as the folding area. We try to investigate the different diameter. If you fold it with different diameter, we definitely large diameter longer cycling time, and short diameter that you will have shorter cycling time. We're trying to solve this problem with a kind of water inside electrolyte. It was reported previously. It was reported that water inside electrolyte can prevent the growth of polymer of the dendrites. But if you even use water inside electrolyte, we still notice that the problem of R dependence. For example, if you fold it, you still have very short lifetime. But if you use very large R value, that you have longer cycling stability. So that means even use highly concentrated salt electrolyte, you cannot solve the problem. We're trying to analyze. There's two issues for the flexible configuration. That one is if you fold it, if you ban it, for example, you have the highly concentrated current density, not electric field here, that will induce the uniform growth of the dendrites. So this one, physically, we cannot solve this problem. If you ban, you got the concentrated electric field. But on the other hand, there's another issue is when you ban it, you use, for example, hydrogen. You use hydrogel electrolyte that you have dissipate between the electrode and the electrolyte. So ideal case, since we cannot solve this chemically, solve this dendrites issue at the flexible cell configuration, we can try to develop a kind of very mechanically strong material which physically prevent the growth of the dendrites, and this material should be very addictive to the surface of electrode to avoid the detachment between the electrolyte and electrode. So we use water inside hydrogel. We polymerize it to a certain molecule weight that mechanically is very strong, and it can be very adhesive to the electrode. You see that after cycling, even after cycling, you see the attachment between the hydrogel to the electrode is still very strong. And generally, even with a different R value, that you still have very good cycling stability. That's depends on the that's really relies on the mechanical robustness of the hydrogel. And recently we noticed that for zinc batteries, typically we fabricated zinc manganese oxide, zinc vanadium oxide batteries, and when you fabricate batteries naturally in a charged state, then you start to discharge. Discharge means zinc will be start to dissolve. That means for in the zinc battery, typically you start from charged states and zinc will be stripped first, then plate back, right? Then we study the stripping process in detail. That start from initial stripping, with the O potential, then nucleation O potential, then for stripping, then for plating, and we start plating, then you will see the second stripping process start from stripping of active zinc to bulk zinc. Then another plating similar shape of start from two stage of stripping of active zinc, stripping of bulk zinc. Then after a certain time that you will have a decreased stripping O potential. That if you look into the details of the structure, that you start from first cycle, you have some pitch. Originally, it's not totally smooth. If you go for stripping, then your surface is getting much more rougher with some dead zinc growth on surface. Then the surface will get a lot of porous zinc accumulation. The surface is getting rough. We call this dendrites. But if you go for plating first, that means the zinc is not by stripping first, it's by plating first. That we study this process, you still have stripping of active zinc, stripping of bulk zinc, and plating with nucleation O potential for the plating. So after a certain time, the behavior will be slightly different. If you go for morphology study, that even surface is not totally uniform, but first the deposition, if you choose a very suitable current, that even you start from non-uniform surface getting uniform deposition first. Then after a few cycles, you see the surface will be still very uniform, although you still have some dead zinc. So this is a very straightforward information. You start from initial stripping and start from initial plating. After a few cycles, you will see the start from initial plating, the surface getting rougher and much rougher than the zinc start from initial plating. That means we always say we use symmetrical batteries. We use zinc is called symmetrical batteries. But when you start to operate symmetrical batteries, one piece of zinc will start to be plated. The other one will stripped it. So after even one cycle, that the initial the so-called symmetrical battery becomes non-symmetrical. Okay, so this is we, according to our observation, we propose that the pre-deposition zinc will be also a strategy to stabilize the zinc. That means you start from zinc before you use it to assemble full batteries. You use pre-deposition, and at a certain amount of the current density, it should be very large. Then the surface getting much more uniform. Then use this kind of pre-deposited zinc for battery or for full batteries, that you will have much better stability. We're also trying to develop different types of organic anode. Use organic materials. It can be much better, although it cannot totally solve the problem, because it provides a kind of frame to store links, to store different metal ions. And also we study pH value. For example, at the zinc size that you have, you can notice that the zinc, the pH value is getting increased during cycling. That will affect the dendrites growth. Okay, so we've been working on this for a pretty long time. We study a few strategies to solve the problem of zinc anode. But it turns out that we noticed that in the community that we're reporting better and better results, but the strategies are all the same. There's no big change for strategy, but the better and better results were reported. So we noticed that we summarize the current density and accumulated capacity here. The circle points is for symmetrical batteries, and this star points is for full batteries. You see that for accumulated capacity for the symmetrical batteries getting very large, the number getting very large. But if you compare with the full batteries, It's much more small. It's much smaller. And if you compare overpotential of reported overpotential, you will also see the quite diversified overpotential. It can be 80 or it can be very small. So we know that there might be some problems. We call it soft shots. And this is one battery. If you do cycling test for a symmetrical battery, we'll use to do this kind of cycling test. And if you see only see the charge curves, it looks normal. But if you check the impedance, then you see originally it's quite normal impedance. But at certain point, for example, F point, that the impedance is getting very small. So in a battery, generally we have a few states. One is normal states as a battery, but the other one, short circuit, is more like a resistance. The other one is called soft shots, that we have battery behavior, and sometimes we have we also have some short circuit behavior with one more resistance being connected series parallelly. So if you check the impedance, this is normal, and this is almost no resistance, but this is you still have the impedance, but generally it's not quite normal. So this one gives us some illusion. It's not normal status, but you can still collect some charge-discharge curves. So we propose a protocol to test this battery. For example, you not only you test the cycling stability, but also you choose a few points to test the impedance. That if the impedance change not that much, although they change with different current density, if it doesn't change that much, generally it should be okay. If it decreases like this, that means your battery is being broken in short circuits. But this one is one suggested protocol. Another one, if you do the cycling stability at different temperatures, you should go to lower temperature instead of increased temperature, because it is soft shots. If you increase temperature, it will melt. They will back to normal batteries. If you go to lower temperature, so for normal battery, it should be like this. For soft shots battery, it should be like this. So if you calculate the activation energy, will be soft charge battery will be negative, but non-battery should be positive. So this is another possibility for you to evaluate your batteries being broken or not. Okay, so I would like to stop now because almost the time. So for zinc batteries. We still have a lot of problems. For example, for anode side, coating is used for additives. If you use different additives, it's also useful. But if you go for large cell, high areal capacity, generally will be not useful. Big problems. And how to rescue a battery, in situ rescue a battery, that's also an issue. For cathode side, manganese oxide, basically we think manganese oxide generally is a deposition mechanism. If you fabricate a small battery, it's good. If you fabricate large size batteries, be a big issue. And conversion reactions provide very high capacity, but some materials are quite expensive. Hydrogen system is permission only when you can immobilize, if you can fissionate the hydrogen materials in some structures. So electrolytes, we can also modify this electrolytes, but generally we claim a lot of wide electrostability window. But if you use it for large scale batteries, you still have small amount of hydrogen pollution. We need to solve this problem. But generally the performance of safety is good. The problem is how to fabricate large size batteries. Okay, advertisement is I'm working on the new journal published by Tsinghua Press together with Professor Xu in the Tsinghua University. We publish different. We are multidisciplinary journals published in the field of energy. Nanomaterial is non-technology for energies. Okay, this is my acknowledgement. So my time is right. I'm right on time. Thank you.
Okay, so thank you very much, Professor Zhi, for your very inspiring work. And so now it's time for the question. So for the audience, so if you have a question, you can either speak out through the audio or you can type in the chat. Maybe I start with the first one. So, Professor, we know that so your group has started a company with the zinc-ion batteries. So I'm wondering, so for the industry application, what's the biggest challenge for the zinc-ion batteries? Because you see in the literature, we see the performance becoming better and better for the real application. So what would be the challenging?
Cycling stability. Actually, zinc-ion batteries, if you compare with lithium batteries, we don't compare specific energy density and also volume energy density because the number of lithium batteries being too high. So we don't compare with this. We choose different application scenarios for zinc batteries, relying on the high safety. So, but if you go for any storage, the problem is, for example, you have flow batteries can sustain over 10,000 times. And some reported lithium batteries, for example, lithium iron phosphide batteries, they claim they can make 6,000 times cycles. These numbers is much higher than zinc batteries. Although we have reported, for example, in our literature for small size batteries can go for 5 and sometimes, or even sometimes we also report even 20,000 times for solid state zinc-ion batteries. But if you try large size batteries, so all these numbers will come that you can only cycle for a few hundreds of cycles. That's a big challenge because if cycle number is low, that means your cost will be high.
Yes. So this cycling stability is related to the electrode materials itself or related to the side reactions in the interface?
So we see all of them at anode side, at cathode side. A lot of side reactions and stability getting much worse. And when you have side reactions, you will notice that electrolyte will be also exhausted because they decomposed. You're getting less and less electrolyte, so the battery eventually will be broken. So we see a lot of problems. Anode side, in some system, anode side, for example, when we're trying to fabricate kind of halogen batteries, if you set the battery to be 70 milliampere hour, you can run for 1,000 times. But if you set the battery, you put a high loading mass for the cathode side to make the battery the same size at 500 milliampere hour, that then the battery can only cycle a few cycles, a few times.
Oh,
so,
okay.
Yeah.
I see. Thank you very much. So if no other questions, then we move to our next speaker. And let's thank Professor again for the wonderful talk.